Today we're going to explore the physics behind espresso extraction. Specifically, how grind size and extraction time control the balance between bitterness and acidity through a process called diffusion-limited mass transfer. Let's start by visualizing a coffee particle. Inside this particle are hundreds of soluble compounds, acids, sugars, oils, and bitter alkaloids. These compounds are trapped within the cellular structure of the ground coffee. Here's the central question we'll answer today. Why does finer grinding produce more bitter coffee, while coarser grinding produces more acidic coffee? The answer lies in molecular size and diffusion. Acidic compounds are generally smaller molecules that dissolve quickly. Bitter compounds like caffeine and chlorogenic acid lactones are larger and take longer to extract. To understand this rigorously, we need to examine Fick's laws of diffusion. This is the fundamental physics governing extraction. Fick's first law states that the flux J of a solute is proportional to the negative gradient of concentration. D is the diffusion coefficient, and partial C over partial X is the concentration gradient. Fick's second law describes how concentration changes over time. Partial C over partial T equals D times the second spatial derivative of concentration. What does this actually mean for our coffee? Let's think about a single spherical coffee particle being extracted. Imagine a spherical particle of radius r. The soluble compounds must diffuse from the center of the particle to the surface, where they dissolve into the water. Here's a critical insight. The time it takes for molecules to diffuse out depends on the square of the particle radius. The diffusion time scales as r squared over d. This is incredibly important. If you double the particle size, the extraction time increases by a factor of 4. Let's calculate some actual numbers. Suppose we have a typical diffusion coefficient for coffee compounds in water at 90 degrees Celsius. A reasonable estimate for the diffusion coefficient is 10 to the negative 9 meters squared per second. This is typical for small to medium-sized organic molecules in hot water. For a fine espresso grind, the average particle diameter is about 200 micrometers, so the radius is 100 micrometers. 100 micrometers equals 10 to the negative 4 meters. The diffusion time is 10 to the negative 4 squared divided by 10 to the negative 9, which equals 10 seconds. So compounds from a fine grind extract in roughly 10 seconds. Now let's consider a coarse grind with particles of 600 micrometers diameter, so radius of 300 micrometers. 300 micrometers equals 3 times 10 to the negative 4 meters. The diffusion time is 9 times 10 to the negative 8 divided by 10 to the negative 9, which equals 90 seconds. This is 9 times longer than the fine grind. This calculation reveals why grind size is so critical. With a fine grind, both acids and bitter compounds have time to extract. With a coarse grind and short extraction, only the fast-diffusing acids extract. Here's a visual representation. With fine grind and 25-second extraction, we get lots of both acids and bitters, creating a balanced but potentially over-extracted shot. With coarse grind in the same time, mostly acids extract, giving a bright, sour shot. There's another crucial factor: surface area. When we grind finer, we don't just reduce diffusion distance, we also massively increase the total surface area available for extraction. The total surface area equals the number of particles n times 4 pi r squared for each particle. If we keep the total coffee mass constant but grind finer, what happens to the number of particles? Total mass equals n times density times 4/3 pi r cubed. If we keep mass constant and reduce r, then n must increase. The number of particles is proportional to 1 over r cubed. So if we have the particle size, we get 8 times as many particles. Therefore, the total surface area is proportional to 1 over r. Having the particle size doubles the total surface area. This dramatically increases the extraction rate. We can write a simplified equation for extraction yield based on these principles. Yield equals Y max times 1 minus e to the negative kt, where k is the extraction rate constant and t is time. The rate constant k is proportional to diffusion coefficient times surface area divided by volume, which scales as 1 over r squared. Smaller particles extract much faster. Let's plot extraction yield versus time for different grind sizes to see how this works in practice. Here are the extraction curves. Fine grind in red reaches high extraction quickly. Medium grind in green is slower. Coarse grind in blue takes much longer to reach the same yield. Different compounds extract at different rates. We need to consider this to understand flavor development. Acids have high diffusion coefficients around 2 × 10 to the negative 9. Sugars are intermediate at 1 × 10 to the negative 9. Bitter compounds are slowest at 5 × 10 to the negative 10 meters squared per second. This difference in diffusion rates creates a sequential extraction. Early in the shot, acids dominate. Then sugars. Finally, bitter compounds extract. This graph shows concentration versus time. Acids in green extract rapidly and plateau first. Sugars in yellow are intermediate. Bitters in red extract slowly and continue rising even at long times. There's an optimal extraction window where we have enough acids and sugars for brightness and sweetness, but not too much bitterness. Under extraction gives sour, thin coffee dominated by acids. The optimal zone has balanced extraction of acids, sugars, and moderate bitters. Over-extraction produces harsh bitterness and astringency. We haven't discussed temperature yet, but it's crucial. Temperature dramatically affects the diffusion coefficient. The diffusion coefficient follows an Arrhenius relationship. d of T equals d0 times e to the negative activation energy over RT, where R is the gas constant and T is absolute temperature. For coffee compounds in water, the activation energy is roughly 20 to 30 kilojoules per mole. Let's use 25 kilojoules per mole as our estimate. Let's compare diffusion at 70 degrees Celsius versus 95 degrees Celsius, typical espresso temperatures. The ratio is e to the quantity 25,000 over 8.314 times 1 over 343 minus 1 over 368. This gives approximately 1.7. So increasing temperature from 70 to 95 degrees Celsius increases the diffusion rate by 70%. This is why espresso machines operate at 90 to 96 degrees Celsius. The high temperature accelerates extraction, allowing short contact times of 25 to 30 seconds. At low temperature, diffusion is slow and we need much longer extraction times. At high temperature, diffusion is rapid and we can extract efficiently in 25 seconds. Many people think pressure directly affects extraction. This is actually a misconception. Let me explain what pressure really does. Pressure has minimal effect on the diffusion coefficient. Diffusion in liquids is relatively insensitive to pressure unless you go to extreme values. Pressure's real role is mechanical. It forces water through the tightly packed coffee bed, ensuring fresh solvent contacts all particles. Pressure forces water through the coffee bed. Without pressure, water would just sit on top. The flow ensures that extracted compounds are carried away, maintaining the concentration gradient that drives diffusion. There's a subtle but important phenomenon called the boundary layer effect. Let me explain this with a diagram. Around each particle is a thin stagnant boundary layer where flow is very slow. Compounds must diffuse through this layer. If flow is too slow, this layer gets saturated and extraction slows down. Higher flow rates and turbulence reduce the boundary layer thickness, increasing mass transfer from particle to bulk water. The mass transfer coefficient equals d over delta, where delta is the boundary layer thickness. Thinner boundary layers mean faster extraction. Channeling is when water finds preferential pathways through the puck. This is disastrous for extraction uniformity. In the channel, water flows rapidly and over-extracts. On the sides, water barely flows and under-extracts. This gives you a mixture of over- and under-extracted coffee, which tastes terrible. Real grinders don't produce uniform particles. They create a distribution of sizes, and this has important consequences. A typical grind has a distribution centered around 200 micrometers, but with tails extending to very fine particles called fines and large particles called boulders. The fines, being very small, over-extract quickly and contribute excessive bitterness. The boulders under-extract and waste potential. This is why grinder quality matters. The standard deviation of particle size distribution is proportional to flavor variance. A narrow distribution gives more consistent, balanced extraction. There's a common rule: if your shot pulls too fast, grind finer. If too slow, grind coarser. Let's see why this works from first principles. Flow rate Q through a porous bed follows Darcy's law. Q equals delta P over mu times K over epsilon L, where K is permeability, mu is viscosity, epsilon is porosity, and L is bed thickness. Permeability is proportional to the square of particle diameter. Finer particles create much lower permeability, slowing flow dramatically. When you grind finer, permeability drops, flow slows down, and contact time increases. This extracts more compounds, especially the slow-diffusing bitter ones. Flow rate doesn't just change contact time. It also affects the concentration gradient by removing extracted compounds from the particle surface. With slow flow, the liquid around particles becomes saturated with extracted compounds, reducing the driving force. With fast flow, fresh water constantly removes extracted compounds, maintaining a steep gradient. Too slow and you saturate the boundary layer. Too fast and you don't give compounds time to diffuse out. There's an optimal balance. We can write a dimensionless number that tells us if we're diffusion-limited or flow-limited. The Damkohler number equals the reaction rate constant times characteristic length over velocity. For extraction, this compares diffusion time to residence time. If Damkohler number is much greater than 1, diffusion is fast compared to flow. We're flow-limited and need higher flow rate. If Damkohler number is much less than 1, flow is fast compared to diffusion. We're diffusion-limited and slower flow won't help. For typical espresso conditions, Damkohler number is between 0.5 and 2. We're in a mixed regime where both diffusion and flow matter. This is why barista technique is so critical. Small changes in grind, dose, temperature, or pressure significantly affect the balance between diffusion and flow. Let me give you a practical framework for troubleshooting espresso based on everything we've discussed. Think of flavor as a two-dimensional space. Vertical axis goes from sour to bitter, controlled by extraction time and temperature. Horizontal axis goes from weak to strong, controlled by dose and ratio. If your shot is sour, you're under-extracting. Grind finer to increase contact time and surface area, or increase temperature to speed diffusion. If your shot is bitter, you're over-extracting. Grind coarser to reduce contact time, or lower temperature slightly. If your shot is weak or watery, increase your coffee dose or reduce your output volume to increase concentration. If your shot is too strong or muddy, reduce dose or increase yield. Can we write down the equations that would predict the perfect espresso? In principle, yes. In practice, it's extraordinarily complex. For each compound I, we have the convection diffusion equation. Partial Ci over partial T equals di times the Laplacian of Ci minus the velocity field dot gradient of Ci. We'd need to solve this partial differential equation for hundreds of different chemical compounds, each with different diffusion coefficients and solubilities. And we'd need to solve it in a complex three-dimensional geometry with spatially varying flow patterns that depend on the puck structure. This is why, despite all our physics and mathematics, espresso making remains as much art as science. The system is too complex for complete analytical solution. Let me summarize the key physical principles we've covered today. First, diffusion is the fundamental rate-limiting process. Compounds must diffuse from inside particles to the water. Second, diffusion time scales as the square of particle size. Having particle size quarters the diffusion time. Third, acids diffuse faster than bitter compounds, creating sequential extraction and the possibility of balanced flavor. Fourth, total surface area increases dramatically with finer grinding, further accelerating extraction. Fifth, temperature has an exponential effect on diffusion rate through the Arrhenius equation. Sixth, flow rate affects extraction by modulating the boundary layer thickness and removing extracted compounds. Seventh, pressure's primary role is mechanical, forcing water through the bed, not directly affecting diffusion. Eighth, Particle size distribution is critical. Narrow distributions give more uniform, balanced extraction. What I find beautiful about this system is how it connects fundamental transport phenomena to sensory experience. We go from Fick's laws of diffusion, written in 1855, to the taste of your morning espresso. The same physics that describes oxygen transport in your lungs describes coffee extraction. The next time you pull an espresso shot, think about the billions of molecular collisions per second, the concentration gradients driving mass transfer, the boundary layers around each particle. You're not just making coffee. You're conducting a sophisticated experiment in multiphase flow, diffusion-limited mass transfer, and chemical kinetics. Let me leave you with some questions to think about. How would espresso extraction work in microgravity? Without convection, would we get pure diffusion-limited extraction? Could we use ultrasonic agitation to disrupt boundary layers and enhance mass transfer? This is actually being explored in some experimental machines. What's the theoretical maximum extraction we could achieve given thermodynamic solubility limits? Are we close to the limit, or is there room for improvement? Thank you for joining me on this deep dive into the physics of espresso extraction. I hope you now see the beautiful complexity hidden in your daily cup of coffee.